Welcome to This Explainer. Today, we're diving into a revolutionary piece of tech that's quietly transforming the literal foundation of modern computing. Now, if you work in tech, there's a really good chance you've interacted with this technology today without even realizing it. It's that pervasive. We're going to break down this complex system architecture together, and by the end, this highly technical evolution is going to be incredibly easy to grasp. Let's dive right in. So, for decades, we've pretty much viewed the Linux kernel as a rigid, static entity. It was essentially a closed box, right? It managed your hardware, it ran your applications, and fundamentally changing how it behaved was, well, an absolute nightmare. But did you know Linux is secretly evolving into a programmable operating system? It's undergoing this massive, silent transformation. And the engine driving this profound shift is a core technology known as eBPF. The biggest players in the tech industry are absolutely obsessed with the secret superpower. We're talking Google, Meta, Netflix, Cloudflare. These giants are relying heavily on eBPF to run their massive, globally distributed infrastructure. And they aren't just experimenting with it in a lab somewhere either. It's fundamentally baked into how they scale, secure, and optimize their systems at a level most companies can't even fathom. Look, when you're dealing with millions of requests per second, traditional OS limitations become massive bottlenecks. If the largest tech companies in the world are betting the farm on this tech to solve those bottlenecks, we definitely need to understand exactly what it is. Okay, so here's our roadmap for this explainer. First, we'll track the secret evolution of Linux. Second, how this tech hooks into everything. Third, disrupting traditional networks. Fourth, a totally new security paradigm. And finally, the future of cloud-native environments. All right, Section 1, the secret evolution of Linux. From a simple packet filter to a fully programmable OS. To really appreciate where we're at today, we got to look at where this all started, because the origins here are surprisingly humble. eBPF stands for Extended Berkeley Packet Filter. Years ago, the original BPF was just a basic tool built into Linux. Its only job was to look at network traffic and ask one very simple question: should this network packet enter? That's it. It was the tech powering early network analyzers like TCP dump. But then, Linux kernel engineers had this massive light bulb moment. They realized, hey, if we can safely put dynamic code directly into the core kernel execution path just to filter network packets, why not use that exact same concept to do almost anything else? Think about the sheer contrast between the old world and the new world here. Traditionally, changing the kernel meant writing a custom kernel module, and this was incredibly dangerous. If you made one tiny mistake in your C code, you wouldn't just get a simple app error. No, you'd cause a full-blown kernel panic, corrupt system memory, or crash the entire machine. Imagine getting paged at 3 a.m. because your custom module took down a massive production node and you have to completely reboot the server just to fix it. Now compare that to the elegance of eBPF. You can dynamically inject these small, highly focused programs into the kernel on the fly. No reboots required. And best of all, it's completely safe. But you're probably wondering, how exactly does it guarantee that safety? Well, the secret sauce is the eBPF verifier. Think of the verifier as the absolute strictest bouncer at the most exclusive club in the world, the Linux kernel. Before any eBPF program is allowed to run, the verifier thoroughly analyzes the code. It ensures there is zero illegal memory access. It proves, mathematically, that there are no infinite loops that could accidentally freeze up your whole system. It explicitly blocks any dangerous operations or out-of-bounds behavior. It essentially predicts exactly what your code is going to do before it ever runs. Only perfectly safe, verified code is allowed inside. And that gave Linux, for the very first time in its history, safe dynamic programmability. Moving on to Section 2, hooking everywhere in Linux for complete system visibility. Safely running code in the kernel is awesome, but eBPF's true power lies in its ability to attach to almost any event happening anywhere within the operating system. It offers unprecedented hook locations. You can attach programs to the network stack to perfectly monitor all TCP, UDP, and DNS traffic flowing through the machine, analyzing packet drops in real time. You can hook into system calls. That means every single time any application tries to open, read, or write a file, eBPF sees it instantly. You can attach to the CPU scheduler to analyze exactly which processes are hogging CPU cycles. You can even hook right into the file system to see exactly who deleted a specific file or which rogue app is causing a massive spike in disk I/O. It's literally like having X-ray vision into the deepest levels of the machine. And this isn't just theoretical stuff either. Take Netflix, for example. They heavily leverage eBPF via the CPU scheduler. When you're dealing with global streaming at their monumental scale, a tiny microsecond delay in the infrastructure can cascade into a massive user issue, resulting in that dreaded buffering wheel on your TV when you just want to watch a movie. By hooking deep into the scheduler, Netflix engineers can actually analyze latency problems and pinpoint exactly which threads are stuck. And they do it in real time, right in production, without slowing down the servers at all. It's wild. Okay, Section 3, disrupting traditional network architecture and the massive need for cloud-native speed. Look, as our infrastructure moved to incredibly complex environments like Kubernetes, the old ways of routing network traffic fundamentally broke down. In a traditional Kubernetes environment, a single network packet has to run this massive, tedious gauntlet. It goes through IP tables rules, connection tracking, network address translation, and complex overlay routing, just to get from point A to point B. Think of traditional IP tables like a super long, frustrating airport security line. If you have a large cluster with thousands of routing rules, every single packet has to wait in that line and be checked against Rule 1, Rule 2, Rule 3. You get the idea. In modern cloud-native environments where hundreds of microservices are constantly talking to each other, this massive chain adds completely unacceptable latency. But eBPF offers a dramatic solution: XDP, or Express Data Path. XDP is arguably one of the most terrifyingly powerful capabilities of eBPF. It allows you to run your eBPF programs directly at the network interface card driver layer. This means you're processing, routing, or dropping network packets before they even enter the Linux network stack. It saves a massive amount of CPU cycles. Going back to our airport analogy, XDP acts like a TSA pre-check agent standing all the way out in the airport parking lot. It literally bypasses the entire traditional OS security and routing line for ultimate hardware-level speed. In the real world, this translates to massive performance gains. Cloudflare, for instance, uses XDP to drop malicious DDoS attack packets with ultra-low latency. Because the packets are dropped right at the NIC driver layer, they can handle millions of packets per second, practically at the speed of the hardware itself. Meanwhile, modern networking tools like Cilium use eBPF and XDP to completely replace the clunky legacy components of Kubernetes, like kubeproxy. By handling routing, load balancing, and security policies directly in the kernel fastpath, Kubernetes network performance is just dramatically accelerated. Which brings us to Section 4, a new security paradigm driven by deep kernel observability. Because eBPF sits at the absolute bedrock of the operating system stack, it fundamentally changes the game for cybersecurity and threat detection. This total visibility builds an airtight security net. Say an attacker tries to execute a container escape. eBPF catches it instantly through real-time monitoring of abnormal process boundaries. Or if a hacker manages to spawn a malicious shell inside a compromised app, eBPF detects the unauthorized system call the exact millisecond it happens. Privilege escalation, eBPF is already tracking the unauthorized file access. The true beauty here is that attackers simply cannot hide. They might bypass your high-level application security, sure, but they cannot evade the kernel. Because eBPF has total visibility into every system call, the attacker doesn't even know they're being watched. This is exactly why heavy-hitter security tools like Falco, along with modern endpoint detection and response platforms, are moving completely over to eBPF. They utilize it for invisible, real-time threat detection in highly complex Kubernetes clusters. It's a security layer that operates entirely underneath the containers, making it practically impossible for malicious actors to disable or spoof the monitoring tools. They're essentially operating in a house where the very foundation is reporting their every single move. Finally, Section 5, the future of cloud native and the emergence of kernel as a platform. We're really moving away from thinking of the Linux kernel as just some background software that manages hardware, and instead viewing it as a dynamic, extensible foundation. The eBPF ecosystem is expanding rapidly, fully enabling this kernel as a platform concept. It underpins a massive wave of next-gen tools: Cilium for networking, Falco for security, Pixie for rich observability, and Catron for robust load balancing. There's even a brilliant tool called bptrace that lets engineers write simple one-line scripts to trace complex kernel behaviors instantly. Now, look, it's not magic. It does have limits. To protect the kernel, the verifier enforces a small memory stack and strict safety loops. But honestly, these very constraints are exactly what make it a safe, rock-solid platform for infrastructure innovation. And that brings us to this massive paradigm shift. Linux is no longer a closed black box. It has become observable, programmable, and analyzable in real time. What was once dark and rigid is now completely illuminated and deeply flexible. It allows us to dynamically alter the behavior of the operating system on the fly to build faster, safer, and infinitely more efficient infrastructure than ever before. So I'm going to leave you with a final thought to chew on. As eBPF continues its rapid evolution, moving way beyond just networking and security, how will it completely redefine what an operating system should look like in the era of cloud and AI infrastructure? We are truly just scratching the surface of what a programmable kernel can achieve, and understanding eBPF puts you at the absolute forefront of where tech is heading next. Thank you so much for joining this explainer, and keep exploring.